Here with me there is Thorsten Böllinghaus. Is correct, the pronunciation is perfect. Okay. Thorsten is a Chief Technology Officer at Bowel AG from Germany. Prior to do that, he worked for many years in the Saint-Gobain Group at the various locations, including as a production manager and later as a plant manager. Okay, we are grateful for his presence, and let's welcome to Thorsten.
Thank you very much for the introduction, and it's a pleasure for me to speak to you about the cutting with cutting wheels, because many things can, if they're done correctly, you can bring it to the level of laser cutting, and this is what we want to talk about, how to manage the cutting and to reduce the waste you can have in the cutting process itself, and especially in the subsequent processes and even on the final product. So what's the overall goal for cutting? It is for sure cutting and breaking along the desired lines. It is because you don't want to have any glass losses during cutting and breaking. You don't want to have pictures as you see on the top right. It's to have low geometrical losses. You want a good trim. You don't want any over or under breakage, especially because of the grinding times you have later. You don't want flakes or splinters on the glass, not only for the sake of the splinters and themselves, but also, we'll come to that later, because where the splinter was before, you have harmed the glass, and this is bad for the stability of the glass. And we want a high strength of the cut glass pane, because we don't want to go to our customer and exchange a glass. And the glass cutting has an important influence on the final product. So why do we do this? Already in raw glass production, costs are very high. But even more if you do coating, tempering, laminating, for sure, all of you know. If you have to flood a compartment in your coater, or if you have a laminated glass that has been coated and you destroy it, this is very expensive. Economically, even worse is when you have to visit your client and exchange a window, as you see on the left picture there. And as glass production is extremely energy intensive, each loss has a major CO2 footprint. So we want the opposite of what we just saw, and we want glass cutting like you see on the right side. It is obvious that glass cutting with cutting wheels consists of the two steps of scoring the glass, which we call cutting, and then breaking it later on. And the first part is very often called cutting, so that's what we want to use as vocabulary. Now, what happens when you score the glass? What you want is what you see in the picture. That's what you don't see with your eyes. That's the tensions you bring in the glass and the median crack you don't see here. What you don't want is what you see, which is the damage you do to the glass surface. And that's an important thing to understand, that the glass surface damage is something we have to accept, but it is not something that we want. So now, what is the cutting force influence of the glass cutting? You need a certain cutting force, because if your cutting force is too low, you will not break the glass. If your cutting force is still too low but higher, it will not break along the desired lines. If you have the right cutting force, everything is correct, and if you have a too high cutting force, then you get the splinters that we don't want for several reasons. Very important for the cutting force and the cutting pressure is the right dimension of a cutting wheel. And this is very important to understand, so we will talk about this a little. And the most important dimensions of the cutting wheel is the outer diameter of the cutting wheel and the angle of the cutting wheel. Because, as you can see here, if you have a bigger cutting wheel and at a given depth that it touches into the float glass, then you will get a larger imprint of the cutting wheel. And the same is true for another cutting wheel angle. And why is this so important? That's why what I will show to you now. It is as the contact zone. In the contact zone of the cutting wheel with the glass surface, you have the cutting pressure. And if now your cutting force, which you divide by the contact zone, the contact area, the surface that you have with the wheel, with the glass, is too high, then you will damage the surface of the glass. That's what you see here and there. The higher the force is divided by the contact zone, the more you damage the glass surface of the wheel. What we want, as said before, is we want to bring the tensions into the glass. So if you look at the equivalent formula and now you say, okay, I don't want to raise my cutting pressure too much because I don't want to destroy the glass surface too much, but I need a high cutting force to bring the tensions into the glass. So if this is limited, then you have to raise this if you want to raise your cutting force. And this is very important to understand. And this is on many production lines not so well understood. So this is an important thing to keep in mind, because I said here is the pressure at the surface too high, you will get splinters and damage your glass. Why is this so? If your cutting wheel touches the glass, you bring in the stresses. And if you relieve it when the cutting glass has passed by, then you will also get lateral residual stresses that later on lead to lateral cracks that you don't want. So we don't want the shattered zone, we don't want the lateral crack. The only thing we need is the medium crack and is the tensions you bring to the glass. Because if, again, the pressure is too high on the surface, you will get the flakes and you will get a reduced edge strength stability of the glass panes. Matthias Seel this morning talked about a project that was done University of Darmstadt together with Bohle and other companies where edge stability was analyzed and the influences you can have on the edge stability. And for those who have not participated in the very interesting speech of Matthias Seel this morning, the result of the study, so it's a statistical study between all the parameters you can have in glass cutting and what is the result on the 4-point bending test, which gives you an indication on the edge strength of the glass. And the result is that the main influence factors you have on the edge stability of the glass is the type of cutting wheel and is the cutting force. So you need a certain cutting force for sure to do the cutting, but above that level, a lower cutting force is better for the edge stability of the glass. Another important point is the grind of the glass that you can have, which gives the roughness of the glass. On the upper picture you see a very rough grind, and on the picture below you see the roughness profile. This has to be very well controlled because it's like riding on a bumpy road, but it's vice versa. The wheel is bumpy and the surface is flat. You give pressure peaks to the glass below and you get a much more aggressive cut when you cut like this. So if you have to induce high strengths to the glass, high tensions to the glass, then you will choose a grind like that. If you have in a very low sector and you have very thin glass, then you will rather take a grind like you see in the middle. This has to be very well controlled, and so the production of the cutting wheels, the process parameters need to be very well controlled, and quality inspection needs to be very tight. So now the important question was, how now can we reduce the overall cutting force and still create a median crack? And this is the idea is of the generation of a large number of microscopic spots with locally high stress initiation. It is a little like the high heel effect, you can say. So if you compare a lightweight person with high heels and you compare an elephant or me, you can imagine that the high heel has more effect, even the person is much lighter. So the idea is to bring in the tensions, locally very high tensions into the glass. At the same time, the overall cutting force is heavily reduced. And very important is, because you don't want the glass breakage to go into various directions between two indentations, is to give it a linear orientation to help it. So very important is that you have a recessed cutting edge that guides then the breakage later on. And that's what you see on the upper picture here. It's the recessed cutting edge. Now here you can see how this structure you see here can be produced with a laser. What you see here looks rather simple. The slots you see here on a cutting wheel, but in fact it is the recessed cutting edge that is produced here in the gaps in between. So if you look now, what does this to the glass? Compare this classical wheel you see on the left with a continuous cutting edge, and you have a wheel with recessed cutting edge, which is microstructured in the middle. And there are other techniques, like having a cutting edge with just an interruption in the cutting edge. That's what you see there for comparison. And you see here there's an interruption, so the cutting edge is not going through, and here you see the cutting edge that is continuous. What does this now in difference in the glass imprint? You can see here, that's the linear effect that I was talking about before. You want between two indentations, whereas if you don't have the recessed cutting edge that is continuous, then you get a side wing effect you don't want to have. So if you now do a cross cut, that's what you do for the evaluation of glass, and look at it from the top, that's what the classical cut looks like, with the side effects and the radial cracks and things like that come with a normal classical cut. And you compare this to the recessed edge microstructured wheel, you see this perfect image you see there. And also you see that if you don't have the continuous recessed cutting edge, then you get the side effects that are almost similar to those of a classical cutting wheel. And also when you break the glass, then later on, you take the cross cut and you break it, you will see what you then expect from the picture before. You see that on the left side, the classical cut is a little eaten. You see the very nice picture of the recessed cutting edge, and you see that the cutting edge that is not continuous doesn't give the same result. So very clearly, the advantages of a microstructure cutting wheel with recessed cutting edge is the excellent edge qualities, the minimal cutting force, which is also good for ultra-thin glass. So if roughly 1/3 less cutting force you need, it is minimal splintering and the improved edge stability. Now another question is, what material would you choose for your cutting wheel? And to point it out, the choice of cutting wheel material is rather a question of service lifetime of your wheel. It is less a question of the cutting in the beginning when you start your cutting. So it's a question of service lifetime rather. Materials there are, historically it's steel. You don't find in industrial cutting, you don't find steel anymore. So most commonly you have the tungsten carbide, which is the big blue thing. And if you compare wear resistance, which is hardness, and the toughness, that's the zone it covers. Toughness is very important because in industrial glass processing, when you're not in the laboratory, you can hit your glass very with high impact. So for the stability of the cutting wheel, it's important also to have the toughness of a wheel. So cemented carbide or tungsten carbide covers quite a zone, and cutting wheels are rather in the upper part or in the highest part of it. And you can also choose diamond, polycrystalline diamond for it, but which has a much longer lifetime. We'll come to that later on, but which has a is much more expensive. The material is much more expensive than tungsten carbide. So one idea was, how can a compromise be found between the two? And the idea is that you have a hard coating on the cutting edge to enhance lifetime and conserve the properties of the wheel. You have on the left side of the picture, you see a classic cutting wheel, and just beside you see a hard-coated cutting wheel, which is done via some gas phase process. And what you see in the picture here is also that you have an ultra-thin coating, and the properties of the wheels are conserved. You still see the grinding structure and everything of the wheel, and this way you can enhance the lifetime of the wheel dramatically without using the very expensive material of diamond. So this brings us to Yeah, a graph we intended, it's a simplification of the different cutting type technologies. To understand things, simplification often is important and is useful. So it doesn't, for sure, does not cover all aspects, but it puts everything into 2 dimensions, which is the cutting quality you have on the y-axis and the cutting distance, so the lifetime, you have the x-axis. And now if you look on the lower part, on the carbide wheel, it has the wear and lifetime conditions and properties as they are. So if it goes down, doesn't mean that you can't use it anymore. Normally in your normal process, you raise then the cutting force or you adapt your parameters so that you compensate this. But in the end, it wears and you have to counteract this. Then the yellow line is the diamond wheel, which has a much longer lifetime. And what is interesting also, it has very stable conditions in the beginning. So the line wants to indicate that you don't have to modify your cutting parameters so quickly. So this can be interesting. And in between is the carbide hard-coated wheel. It's really in between of the 2. And this can be very interesting also if you have, like if you cut glasses which are very expensive, as we said. If you have a laminated glass that has been produced on the float line, which has been cut, which has been coated and then laminated, and you damage it, this is very expensive. And when do you change normally your cutting parameters? You change them once you discover problems, but you don't want to discover these problems very often. So you take a cutting wheel that creates very stable conditions for a very long time, and this can be a good application for this type of cutting wheels. With the laser structure, with the recessed cutting edge, you are on a completely different world in cutting quality. That's indicated by the higher level you see on the left side. And as you see, the structured carbide wheel, it has a slightly longer lifetime than the classic carbide wheel. So there are clients that use it for a very long time. You can, but later on it will just have the same properties as a normal wheel, and that's not why you use it. So you use this carbide wheel because you want these extraordinary properties, so you would change it. It has a higher lifetime, a little more than the normal carbide wheel, because you need less cutting force, and less cutting force means less wear. Yes, but it's not a lifetime question. It's using this type of wheel is the question of having completely different cutting properties and getting completely different results during the cutting of your glass. And for sure, if you combine the material and the recessed structure, then you get the PCD laser structured wheel. So I come to the conclusion already. So what is important to understand, that glass cutting does not have only influence on the cutting process itself, but on the stability of the glass you cut, so also on further production processes and on final product. That's very important to understand. The main influence factor during on the losses during cutting and the stability of the glass pane are the choice of the right type of cutting wheel and a suitable but low cutting force. Answering to the choice of cutting wheels, you have to take the right angle, for instance, especially, and the right diameter. You have to take the right surface structure and the right grinding, a microstructure if applicable, and if necessary, the right material and a coating, and respecting a suitable but low cutting force. One way, apart from choosing the right cutting wheel, is then using a microstructure with recessed cutting edge. So this is it. I hope this was interesting to you, and I'm very open to questions from the audience.
Thank you, Thorsten.